So I'm a new person to this conference. I wasn't invited here before. I'm very glad to be here with all of you. And because of that, I might be unfamiliar to many people here. So I've decided to do a bit more extended introduction about my own story of APL, what I like about it, and what I use it for. So let me start with talking about who I am. I'm a student at the Saarland University. It's a university of the state of Saar, which is somewhere on the border of Germany with France. And I've been an intern dialogue, as Tina said. And when I was at Dialog, I was just a C programmer. And my main use of APL is all of its applications to mathematics. And on my blog post, I recently posted about a lambda calculus evaluator and parser and lexer in APL. I've also posted numerical methods, such as polynomial solving and linear algebra. And APL has really soaked into my own personal projects. I was joking with my friends that even if Dialog didn't pay me for doing all the job, I would still be doing it myself in my free time. So I wrote my own APL implementation, like almost everyone who knows systems languages and is interested in APL. So my story starts in 2018 when I learned about the J programming language from IRC, from the channel that was dedicated to J software. And the story goes that there were two people arguing about a mathematics problem. I don't exactly remember the domain of that problem. I think it was combinatorics. But anyway, they were verifying their partial solutions using J, because the channel had an execution bot for J, so they could in real time see the answers to the questions they have posed. And I wasn't really very successful in learning J. That was very impressive to me. But it only took Adam in summer of 2020 to give me a very brief introduction to APL. And we have met in person in spring of 2023 in Saarbrücken, because Adam was attending a conference in Bingen. It's a city very close to Frankfurt. It's approximately 2 hours away from Saarbrücken, so we met and we talked. And he suggested me that I could become an intern, and I interned here. So because I like math, I'm going to introduce myself using numbers. I was born in 2004, and I'm 19 years old. And I started programming in 2010, when I got my first computer. I started learning English by myself, and I learned C++ from a very old book I found. So my first noteworthy program that I wrote, I think, dates to 2015. It was a crossover of Norton Commander and the Inferno operating system from Bell Labs, if you're familiar with that. Then came 2020, and that's the year when I was introduced to APL by Adam. So I was very active in code golf communities, and seeing all those golfy solutions for problems in APL was very refreshing. It reminded me of something. So I decided, OK, now I've got to learn it for real. So I started learning APL as my own personal project for story developing, and I was, I think, becoming a way better programmer ever since I learned APL. So in 2022, I have graduated high school. I was 17 when I wrote my high school finals. And that marks the actual first piece of C software I wrote that I was very proud of. It was a statistical data compressor that used context modeling, which is like a very, very simple backpropagation neural network, to compress data. And if some of you read the Linux mags, you might have heard of it. It's BZ3. So in 2023, I became an intern at Dialog. It was a great experience. So what have I done at Dialog? Well, the list is very long. But it starts with the APL array notation, which is what we're going to talk about chiefly during this presentation. So I have implemented two I-beams. There is a chance that they will be present in 19.0. And I think that they will be the only features that you will be able to use in 19.0 from all the lists that you're going to see in a second. So if you're wondering about the I-beam choice, if some of you are familiar with lambda calculus, And look at my initials. They're KS. And K and S are ski calculus combinators. If you route them out as lambda terms and convert them to binary, you get this number. So another thing that I made and I was going to talk about is quad diff. So I made an automatic differentiation tool for Dyalog APL, which is implementing interpreter as the C code. It can differentiate real and complex functions, but we're going to talk about that later. I've also implemented reverse compose, which was scheduled to be in 19.0, but it didn't quite make it. We'll talk about that too. And the potpourri that won't probably get to Dyalog ever is just my speedups to various primitives. Everson's monadic dot product, you may know it from sharp APL. So for instance, you see here this expression computes the determinant of a square matrix. Obverse, which says the inverse of a function. Monadic endern or glyphs, so veg and vel, for promoting and demoting. And that means adding a one axis or removing an axis at the end by merging two last axes. So basically increasing, decreasing rank. And there's a lot more. Like I've tried to implement under, like almost everyone else. So let me give you a brief introduction to the array notation. It has been the topic of many, many presentations in the user meeting, but we'll just have a refresher to make sure we're on the same page. It's implemented by BQN. BQN was once upon a time an internal Dyalog project where we wanted to make a modern version of APL without the things that we didn't quite like. So array notation made it to BQN, and the main changes are that parentheses and brackets may contain many expressions that are separated by diamonds. And parentheses may now be empty, so open paren, close paren is now a valid expression. And there are three basic constructs. So this is the list construct that we have. So every element, every expression of this list becomes an element in a new vector. So it's basically like stranding, right? Except more explicit. So this is the high rank array notation, where each expression becomes a major cell. And it's important to say that is a major cell of rank greater or equal than 1 in a new array. And we have the namespace syntax, which reminds us a little of JSON. So we're finally getting the APL version of what JSON is to JS. So there is a rationale for the array notation, for why we are spending so much time on it, right? And Dyalog has been very slowly moving away from having their source code in workspaces. A lot of data is fine in workspaces, right? But sometimes it's just better to have the source code in a different text file. So it's easier to use tools like Git or Subversion or Mercurial to manage your code, because you can actually see meaningful diffs between each commit, what lines were changed, what's different. It's also easy to modify and inspect the code. If you want to check the code in browser, if you have a Dyalog workspace, that's not entirely possible, but storing the source in files makes it possible. There are many other reasons, and they're mostly outlined in Morton's presentations about link. I think that he knows better than me, so I'll leave it to him. And now it's possible to do serialize and deserialize very complex structures. So very weird APL objects, like you can serialize a namespace which has a rank 3 array, a tacit function, a thread and maybe a scripted namespace even inside of it, which is not possible using the standard APL expressions, right? We have to use quadfix to put it in the scope. And also, it's just faster than executing APL, and it allows for a reasonably formatted multi-line array notation, and it makes teaching and using APL way easier. So here's a mental experiment. Imagine that one of your coworkers is asking you, hey, I just heard about that APL. Can you explain it to me? And then you have two choices. You either start with the squiggles, the symbols and what they do, or you start by explaining the array model. So what if you want to start with the squiggles, right? It's more hands-on approach to APL. But say that you want to show, for instance, how monadic comma works, right? Ravel. To show how it works, you first need to have a high rank array. And you have to do that using row. And if you want to use row, you also have to explain how it works. It's a very circular reasoning. And another reason is that APL is thought about as a tool of thought and also as a notation. So why is there no notation for the main language construct, which is multidimensional arrays? So let's dive into what actually makes the array notation fast and viable for applications. It's statically parseable. So APL is not statically parseable. We use the Bunda-Gerth algorithm for parsing APL, knowing the name classes of every name that exists in an expression. But this is not needed in our case. So imagine this bit of code. We're going to forget about operators and all that stuff. Let's just think about functions and arrays. So this can be n gets A, B, and C stranded together if they're all arrays, obviously. It can be A and C applied to B if B is a dyadic function. Or it can be C applied to B and then applied to A if A and B are monadic functions, right? It's a little messy. But in the meantime, we know what an equivalent array notation expression means, right? This is always a strand. So another thing that I implement from my internship out of the many, many things is the fast execute mechanism. So because the array notation is a small subset of APL, it uses, I think, enclose and 0/bar to properly write constants that are arrays but have a 0 element in the shape, right? We have to preserve all the other shape elements, but one of the axes has to be 0. So the fast execute mechanism basically can scan for those special constructs that we use in the array notation, and we can determine the value of an expression without actually calling the APL interpreter. So I wrote a very tiny APL interpreter inside of an APL interpreter. And here I have an example. It's a bit difficult to understand. First, let me walk you through it. So x is obviously a vector of numbers, like floating point numbers. Y is just a sequence of APL strings that you could pass to execute, and that would be a strand of strings. And z is just both of them mixed together in random order, pretty much. So here you can see the improvements. We use the IBeam to fix this whole thing. And by worst, it's 31% of performance improvement, and at best, around 2,600. So now I go to the user story. And imagine this scenario. This scenario is actually factual. So I have received 40 megabytes of free-word text and numeric data as a Dyalog component file. And there were arrays, namespaces, a lot of data, quad nulls, just a lot of stuff, right? And the problem is that the customer wants to periodically find differences between the old version of their database and the new version of the database. And also they want to use it with software that is not Dyalog APL. So there are a few possible solutions. We could implement a custom format. We could use JSON. But JSON is really not suited for APL objects. So the actual solution is to use the APL array notation, which has the code name among Dyalog employees as Aplan. The current issue is that the implementation in Quad SE, which is like the default shipped workspace with a bunch of functions supplied by Dyalog, so there's an implementation of array notation, which takes a string and turns into an object, or takes an object, turns into a string. And the problems are that it's very slow. It's not always correct. It has to cross-check. It does not handle a lot of certain edge cases. And there's a bunch of more issues, but there's no point in discussing them. So the solution is to write a very fast deserializer and serializer for the array notation in C and integrate it into the interpreter, right? This is a C job. So let's see at the actual numbers. So here we have at the top, we measure how much time it takes for the current APL implementation to parse all the array notation. So this is 40 megabytes of data, remember? And it takes 8 seconds, 900 milliseconds. And the I-beam takes only 560 milliseconds. That's a very big improvement. And probably the biggest improvement is the amount of workspace used. So as you can see, the serialize in Quad SE uses a lot of memory because it generates a lot of garbage, while the I-beam actually uses not that much more than the fixed data as a string. So to deserialize the array notation, to turn a string into an object, we probably want to take an existing database and first turn it into the APL array notation so that we have something to work with. Well, that proved itself to be very difficult. So here's the story. We have installed the Dyalog on a very powerful machine and set max VS to 100 gigabytes. The input array was 5 megabytes and the output was 9 megabytes. The serializer bundled with Dyalog took 55 seconds to run and needed 16 gigabytes of workspace memory. This Quad SE serializer is far from perfect, but I would like to point out that what it is doing is a very complex task. So for instance, there's a lot of things that are not very clear-cut, like whether it should use APL strands or use the array notation, or how would we format it, or how do we represent weird APL objects, like maybe quad ORs. And well, it's not that difficult to have a bug in it, so it also has to cross-check. So we're going to dive into Quad SE now. What's happening? So here I have two functions. They make absolutely no sense, but they are different, right? You can very clearly see that f is a string plus bound to minus, and g is just two functions bound together. Classic composition. So if we get the string representation of f, that's this. G, same thing. So we can't really rely on the string representation Dyalog provides us, and we have to parse the internal data to determine what kind of a thing have we got on our hands. But surprisingly, all this weird complex logic for handling edge cases is not the bottleneck. It's not what makes it slow. So they say that you have to use the right tool for the job. And to no surprise, APL is the right tool to write a serializer, of course, right? And the certain data types are represented internally by the C code in a very different way than the way you feel it as an APL user, right? But APL is not really the right tool to write a program which takes like a slug of APL array notation and turns it into something pretty, right? Like nicely formatted and everything. So I have written my own formatter as this I-beam, and the memory usage went down by more than an order of magnitude, and the speed was doubled. And let's think about why this could happen, right? So when you think about C, the first thing that you think is that inherently scalar, it usually doesn't overcompute, and formatting an array notation string doesn't really call for any array logic, right? And it's very much a serial problem. For instance, you have to track the amount of open-closed brackets parents. You have to keep track of defense to not accidentally squash them, because that will break many things. So it's just a for loop. While APL is array-oriented, it very often overcomputes. So it computes more than it should compute. And processing is performed as very tiny steps over the whole array notation string. So you have this 40 megabyte string, and you call regex1, regex2, regex3 on the string, and then the time starts adding up to a very bad number. OK, so this is the second part of my presentation, and we're going to talk about all the potpourri that I have implemented for Dyalog. So I was tasked with the array notation as my primary intern project, but I finished it a bit too quickly, and I had nothing to do. So this would just be a testimony to what I was doing when I was bored. So QuadDiff is actually not as smart as it should be, or rather, not as smart as I would like it to be. It's based on Taylor series, and we sample a few points around the point at which we want the derivative to be taken. So here we have an example of a thing like that. So we take the first derivative, and we sample 4 points around x. And this is an implementation detail, but the amount of points that we sample is a bit difficult to determine, and it's generally handled by the heuristics in the interpreter. So if you consider more points, then our accuracy will be better, of course, right? But if there's a singularity, like for instance, square root around 0, then the behavior is going to be way worse. So this is obviously more accurate than the central difference method. So we use the definition of the derivative. So we take the limit as delta goes to 0, and then we take the difference between f of x and f of delta plus x and divide it by delta. So here we have an example with quadfr equal to 645. So that's the default mode in Dyalog APL, that's 64-bit floats. And we take the derivative of sine, which is cosine. So we sample the derivative at the point 0.3. And the difference between the numerical approximation and the actual function is very small. It's like, I think that's only a bit larger than the sysfas, so don't worry. But if we increase the precision to dec floats in Dyalog APL, they are 128-bit decimal floats, then the result looks way better. And there is more or less no difference between what we've got and the actual function being computed. So as I said, I had a lot of future ideas, such as implementing the dual numbers. We're going to talk about them later. So they are a bit like complex numbers. So recall that a complex number is just a plus b times I, where I squared equals -1, right? And this new system is pretty much the same thing. Instead of I, we have epsilon. And we say that epsilon squared is equal to 0, but epsilon is not 0 itself. So when we evaluate a function in the dual number system, then we get the value at that point and the value of the derivative. So you could also have complex derivatives and the inverse of quad diff. That would be a bit funny. So here we have an example of, on the left you have the dual numbers. On the right you have the actual derivative you might remember from school. So there's a crucial observation that the real and the dual part are the function and the function's derivative. And we're going to approach complex derivatives now. They're not as useful as real derivatives, but there are a lot of ideas, and I decided I'm going to use the Cauchy-Riemann equations as a proof of concept. So notice that on a holomorphic function, we can approach a point in two different directions, right? Because we're talking about a three-dimensional space. So based on that, we derived those two equations that have been calculated the way that we took the derivative this way and this way, basically. And based on that, we can write a function like this, which can differentiate complex functions using only real differentiation. And briefly about reverse compose. So you know the normal compose very well, and the rules that pertain it. But we also have the reverse compose, which is very interesting. You can see that it's more or less a flipped version of compose. It has very similar workings. However, there is something I really like about it, which is split compose. Notice, we pass alpha to f and omega to h, and we combine it with g. This is a very useful pattern in tacit programming. So here we have an example in the working interpreter, right? We have the split compose, 5 goes to iota, and the vector on the right goes to absolute value, and we just multiply them together. And I don't like the alternatives. So thank you for attending.